Today we will discuss the pictures. You may say, what kind of pictures are they? These are the frameworks of discussing physical phenomena in quantum theory from slightly different perspectives as far as time evolution is concerned. So that is the essential keyword. Pictures means how to formulate equivalent and alternative formulations of a problem by looking at the time evolution from two different perspectives. Essentially, time evolution from two different perspectives. Let me qualify this statement. As it stands, it may not mean too much. Till now, we have seen that there are state vectors, which carries all the information about the system, and we have studied the time evolution of these state vectors in this fashion. As once you specify an initial state at a given time, then you ask the question, what is the state as time evolves from t0 to t? You may say this is formally a solution to an equation of motion. Well, of course, this equation of motion is quite different than those in the classical physics. And we have been also able, by going through this discussion in detail, that the psi of t, the state vector, satisfies an equation of motion of this sort. We have gone through, well, actually the way we have approached the problem is started with this for the time evolution, constructed the operator using the basic physical inputs, which for example, the simplest one of being the preservation of the norms, because this theory is a probabilistic theory, therefore you need to have the states to be normalized to unity, and this is sort of the underlying principle, and based on that we deduce that it's unitary, and then we defined the composition rules, that is, we can go through from a given time to a future time in several steps or a single shot, and they must all, that led us to a composition rule, and etc. We identified the identity corresponding to no evolution case. We also discussed the case that there should be an inverse. If we go in one way, we can nullify that transition by going back to the initial state by the inverse transformation, etc. It enabled us to construct this explicitly via an equation of motion. First, that equation of motion satisfied by the U enabled us to deduce an equation of that sort. I have to confess that this is a little opposite to the conventional or historical approach. People usually, when they are postulating, when they're listing the postulates of the quantum theory, they include the Schrödinger equation, time evolution equation, among those postulates or axioms, whichever you would like to call them, and then go back. But here in this book, it's this opposite approach, but they're perfectly equivalent, so there's no problem as far as understanding it. Well, notice that this is sort of the default framework approaching quantum theory, and so it's called the Schrödinger picture, really. But as you all know, in order to define it more rigorously, we have to also talk about how do the observables evolve in time? Well, in the Schrödinger picture, observables like X and P, well, if you want, let's put the labels so that we don't give you the impression as if we are doing the energy which are derived from them, angular momentum which are derived from them, those quantities corresponding to the classical dynamical variables, really, that's what we are saying, they do not evolve in time. Obviously, I have to really put here, without hiding it to those semicolons, H, the Hamiltonian, the basic, really the most central physical observable in the framework of quantum theory, so H should be there. So do not evolve in time, they are frozen in time. Well, that was sort of tacit or implicit in what we have been till now. From this point on, after some mathematical preparation, we are going to really emphasize these explicitly and emphasize on the distinction between this particular framework and the alternatives which we will meet along the time, in time, along the way. And the basic philosophy is the following. We have seen that if we consider unitary transformations, in general, what are those? We have seen till now several unitary transformations physically meaningful. One are those transformations connecting different bases, different transformations connecting different orthonormal bases, for instance. Well, this was an important problem in this context, and it also has applications in other physical contexts. This is important. We have worked it out in detail, and we have realized that if you have two orthonormal bases, you can transform from one to the other or vice versa, and these transformations are unitary. And okay, there are so many interesting details about them. Second, for example, space translation, which was an important transformation associated with the symmetry of the world, of the space. Space translations were unitary. And also, lastly, most importantly, this dynamical, when we moved into dynamics, we have discussed about the time evolution. That's also unitary, which we have discussed in detail. Notice that behind all these, there is the norm preservation, right? In both space translation and time evolution that was made manifest. And also it was more or less implicitly clear in the first class, that is transformation relating orthonormal bases. When you say orthonormal, norm preservation is more or less automatic, right? The first base is orthonormal, meaning they all have norm 1. The second base is orthonormal, again meaning that they have all norm 1. It wasn't really imposed unitarity, it was sort of by default unitarity. If you go from one orthonormal basis to another, it should be so. So how do we really discuss these unitary transformations? We say if we have a state, well, let me suppress the time dependence, not to give you the impression as if I'm talking about the time evolution only. When you have a state, you go to a transformed state via a unitary transformation of this sort. Then you may also ask the question, If you have such a transformation under consideration, of course, there could be any one of those physical problems that we are tackling. Eventually, we are going to have rotations too when we move into space angular momentum business. So you can really enlarge this class of unitary transformations which are physically relevant. Then you ask the following question. If this is the way these states are transforming, or vectors or kets in a Hilbert space are transforming in this way, how do the operators in this space, there are operators as well, right, along with the state vectors, how do they transform? Well, transformation rule we worked out again when in the introductory, the first chapter, when we were working out the basic mathematical principles, that is physics in a linear Hilbert space, vector space for the finite dimensional case, Hilbert space in the infinite dimensional case. We have seen that the operators transform in this manner. I don't want to give you the impression, when if you really forget the background of this transformation, you may say, how? Why not, for example, if states are transforming as multiplied by from left by the u, you may say operators should transform the same way as well. Of course, that's funny. I'm joking, of course. Well, there's a rationale behind it. We worked it out, right? How those matrices or operators transform under unitary transformations. Let me give you a quick and very sort of operational, cheap way of remembering this rule. What is the rule? Well, if these are vectors in the vector space, ket space, there are other simple kets as well, right? Eigenkets of those observables, for instance. Let's deal with that. As I said, to refresh your memory rather quickly, consider the following eigenvalue problem, using our old notation of labeling the operators with capital letters and the associated eigenvalues with the letter 1. And suppose it's discrete. If not, we are going to go to integrals, doesn't matter. Say eigenvalues AI and eigenvectors associated with the same notation. If you have a transformation like this one, notice that this is not the most general discussion. The most general discussion was done before. I'm illustrating the rule to remind you why this sort of quote-unquote a rather exotic way of transforming the observables. Well, it's a vector, so we said the rule is that you multiply the vectors from the left to get the transform states. Then how does, for instance, the operator A transform under such a transformation? I will make use of this particular equation in a moment when I move into the Heisenberg picture. It's not on purpose that I have chosen this. It's a simple example, okay? So what do you do in order to have that rule to emerge? You multiply this entire equation, left and right-hand side from left by u, and then you go to this equation. Eigenvalues are numbers. The operator jump over and go there, right? Then what do? I insert an identity in between that space I have left there for that purpose. That's an identity, right? The inverse times the U matrix itself. So what you have in here is that U inverse times U I U. You see, it takes us just only a couple of minutes to reach to this equation. You say, of course, due to the nature that it's an eigenvalue equation, there's an extra feature which followed, forget it. What I'm trying to emphasize is this. If you call it the transformed A, and this one the transformed eigenvector, eigenvalue didn't change, never mind, that we'll explain. So if this is the original equation and this is the transformed equation, and these are how the vectors state eigenvectors and the operators transform. Okay, so what I am trying to get at in here, suppose you have, let me use the book's notation again, not to deviate. Suppose you have the following matrix element. You have the states vectors in that vector space, you have the operators, etc. And consider the following matrix element. It's not an expectation value. In order to have an expectation value, you have to have psi and psi in the same size in the left and right hand side. It's an arbitrary matrix element of x between those states. So you may think of, for instance, transforming the states. Think of some kind of symmetric transformations like those or the others that we are going to deduce further, that psi 2 went to psi 2, that's transformed. And this one went to psi 1, as we know the rules that we worked out again at the first part of this class, that whatever transformation you have in the ket space, in the bra space, the operators are Hermitian conjugated. If they are Hermitian, they become the same, but we are talking about the general transformations and unitary operators. Obvious, they are not Hermitian, they are different sort. U dagger is U inverse, but not U itself. Think of this. So what you have then, the matrix expectation becomes, sorry, let me stick to the operation that I have done. That is, after transforming the states through this U transformation, the new expectation value is this. I can think of this expectation value equivalently as, that is how it went to, as psi 1. It is obviously so equivalent that you may say it is really unnecessary to write it, but instead of sandwiching the original x that I had between the transformed new states, you may say you are really taking the transformation of the U some of you may say, is there any inconsistency between that and that? Don't worry. This is consistent within itself, and the way we have to interpret is going to be different. So you may say you can take this transformed x through this rule between the old states. This is very much like the following. Think of this three-dimensional space and the basic unit vectors I, j, k, and there's a vector in here. You can think of carrying out an active rotation by changing the vector, rotating the vector, keeping the basis vectors to be the same. Or a passive way of doing the same thing is keep the vector the same and transform the space itself by transforming in the opposite direction the vectors. That's the space. Either the space is fixed, so you change your physical vector actively, or passively keep this the same and transform back the basic vector. Transforming back this is why it differs from that original thing. Transforming back, going through U or U dagger. Because the basic philosophy in the context of an eigenvalue equation is telling you that if you are transforming states by multiplying them from left by U, the associated observables to those states are to be transformed as U, A, U dagger, but here there is a compensation. Okay. This is at the background of this changing pictures business, really. I will illustrate, don't worry. We are going to discuss this in gory detail because it's an important phenomenon. And the new picture that I will move into, the so-called Heisenberg picture, will have several interesting properties. Among other technical properties, the most distinctive property will be its kinship with the classical physics. So it has this correspondence principle some way built into that new picture, Heisenberg picture, in which we are going to have the observables carrying all the time dependence, and they will evolve in time, and there we'll fix the states at their values at t equals 0, which then in that case they coincide with the Schrödinger picture states. These are simple words you may say, of course they are. Let's see how we are going to really work it out. Okay. Now I will okay, let me start actually discussing the Heisenberg picture now. At the back of our mind, we have the Schrödinger picture in which all these discussions have been developed before. Start with the time evolution again in the Schrödinger picture. So this is, we start discussing the Heisenberg picture. Heisenberg picture. You may think this terminology is a bit, well, exotic. Yes, it is. But anyway, that's how these founding fathers of the quantum theory have introduced, so we are going to follow their footsteps. Pictures. So what is it? We say if we start from a state at t0, it will evolve to psi of t. Remember we introduced this slightly exotic notation. It's less exotic than the one in Sakurai, but still is, saying that this state has evolved from a previous state which was introduced at t0. But eventually we are going to drop those. But here at this level, I have to remind you that notation, that there was this u, t0, and in order to now make the distinction manifest from this picture to the other one, we will temporarily introduce the subindex S, meaning S Schrödinger. But when you have no label, it means default picture Schrödinger. Okay, that's well understood. But just at least at this level of definition, psi of t0 is Schrödinger. Now we said, you know, in the previous discussion, when we were not distinguishing the different pictures based on their the dependence of the states and observables on time, when we were not distinguishing that, we were not making that point clear. But when we are in the Schrödinger picture, now in the Schrödinger picture, observables are frozen in time. You'll see the reason why I sort of emphasize this point. Because in the general discussion of time evolution, we have seen that there were three different cases which appeared. H is time independent, H is time dependent but H at different times commute, and third case, H was time independent. We didn't really talk about pictures. We said as H is Hamiltonian, is the most central object in quantum theory, suppose based on that feature of H, how does the time evolution look like? Here I emphasize, we are in the Schrödinger picture, observables are frozen in time, meaning X, P's, H, angular momentum, all those observables are frozen in time. But external quantities like a vector field at some point, the electromagnetic vector field, which is treated classically, of course that rule doesn't apply to it. It's not an observable. That's a classical field, classical C number field which depends on the position operator itself. If position operator doesn't depend on time, that is consistent with the Schrödinger picture, but the A itself may have a time dependence. So we'll also take that into account eventually. That is one of the subtleties associated with this picture, usually overlooked, but I would like to invite your attention to it. Observables are frozen in time. Thus, H is frozen in time. Thus, the U in the Schrödinger picture, now putting the label in, is known to be this. We have, remember, constructed this in two ways. When H did not depend on time explicitly there without saying, without giving them any name that it's Schrödinger picture or not, this was the result we have obtained. So notice that this operator has quite a nice form. In the context of that discussion I have introduced, we may really raise the following question. If the states are going through that way, what if I take the Schrödinger picture observables X, P, H, L, whatever I collectively call them A sub S, if I transform it in a compensating way as we have done there, we said this expectation, this matrix element we were considering, suppose states were transformed in this manner, and you may say if the X associate involved in this game is transformed oppositely, can we think of it as if they are sandwiched in the old case? Yes. If so, then this is very suggestive. We say if we transform the ASs to the following, for the simplicity of the notation, we will take from this point on this time as 0. The initial time is 0. In that case, this bilocality may be overlooked. It will be an operator U of function of t, and the second entry there is referring to the origin of time taken at t equals 0. Then we say this, he uses the notation sort of as a curly U. Let me imitate his. He says if you move this to there and call it the AH, define it to be so. It's a function of, we take it to be a function of time, suppressing the second entry t0, which was taken to be 0. You go to this transformation. Is it really the same as what we have been doing there? Let me repeat that argument, although it is a trivial repetition, but it's such an important thing. Perhaps you may say this is a justification of going, justification of this transformation from the Schrödinger to a new picture. Instead of saying that I introduce the following unitary transformation. I follow the usual transformation rules that we have defined. I act on the states, call them the transform states. I subject all the observables to the same transformation. And we say, here is the Heisenberg picture. Let's check indeed that the states are frozen in time and the observables now satisfy a new equation rule, new equation of motion, which is very much like the same, if you don't know it, forget it, very much like the same as the classical Hamilton's equations in the classical mechanics, very much like that. But anyway, that's another approach not followed in this book, so I follow his footsteps saying that, is this really the same as that? Indeed so. We have, for instance, this, A at time t. Suppose you consider the expectation value of this Schrödinger picture and Schrödinger picture and Schrödinger picture. The default picture, it's labeled now properly to remind you that it's a Schrödinger. And how did we evolve? We evolved u t0 sub psi 0 Schrödinger, and this is AS, and U this time, U dagger, therefore U dagger T, psi Schrödinger. This is equal to that. I haven't done anything. I have just introduced the time-evolved states expressions in terms of the states at the origin. So this is the same as that, saying that Schrödinger picture when the observables are frozen, this is the expectation value. Now, this is the way which you go to this new picture. If you call this the AH of T now, and these are identified to be the psi of that new picture. Sorry. You have an origin of time. You say the state at that t equals 0 are frozen, and they are taken as the states, frozen states of the new picture. Equivalence is seen. Physics would not be affected by this unitary transformation, and being unitary, they are norm preserving anyway, and all the expectation values or matrix elements, any representations are same in both pictures. So you are free to use this new picture in addressing physical problems, depending on the nature of the problem and depending on the need of the approach. You can, of course, solve any problem in one picture or the other. The physics should be insensitive. They should be the same. You may say, why? We'll see. We are going to elaborate further on it, of course. And then we'll make use of these new formalism in addressing several problems that we have seen before in the other version. And you'll see the advantage of it. Although you may say some of these things I will list briefly are redundant, still it needs to be said. So how did I define? Look at that very pedantic discussion. How did I define the Heisenberg picture states? I defined them as the 0, therefore, it is, how do I get this from there? I get it from there by taking this T, psi T of Schrödinger. I'm repeating, rewriting what is more or less automatic, what is more or less implicit up there. So this is the definition of it, right? Because I said psi t has evolved from this original value. I fixed that original value of this Schrödinger state to be the Heisenberg. So I'm inverting it and writing it as such. What is it? E to the I over h bar h t. Time evolution is e to the minus I over h bar ht, and t0 equals 0, so it is inverse of it is plus. Then what about the A Heisenberg? Now this time we know that it is time dependent. It is U dagger T, A Schrödinger U T, which is, if you want to see explicitly, T HS e to the minus I over HT. So I read from that justification section that the states are defined in this manner and observables are defined in this manner. And do you think it is necessary or is trivial to check indeed there now that these new states are frozen in time? It doesn't do any harm. Let's check it in half a minute. Well, a little more than that, perhaps 2 minutes. that indeed these states are frozen in time, although we said that they are identified as the psi of 0, which do not depend on time explicitly. But how is it? Is it easy to check from that definition? Indeed so. d by dt psi h d by dt e to the I over h bar ht psi t Schrödinger, right? That's the definition in this first line. And you act on the first factor, bringing down I over h bar h times the e to the I over h bar ht times psi t Schrödinger. Next, e to the I over h bar ht times d by dt psi t Schrödinger. Sorry for the simplicity of this argument, but it is as simple as that, really. So what is this? Use the Schrödinger equation as 1 over I h bar h on psi of t s, and compare these two terms. Well, these two terms look similar, but not identically the same. I'm joking, of course. Some of you have realized. Well, here in this one, it's h times the exponential of h. In the second one, it is exponential of h times h. But you know by now, as we have worked it out, the functions of operators commute with that operator. Any function of an operator commutes with itself. How do you demonstrate? You expand it in Taylor series, this exponential. Each term is constant. That's 1, a squared, a cubed. 1 commutes with the a commutes with the a squared commutes with the a using the decomposition rules. So these exponentials commute, and this have I over h bar, this has 1 over I h bar, which is minus I over h bar. These two terms cancel, and you get 0. Nice. But you say, of course, this was trivially expected, right? This demonstrates that the new states defined through this manner, through the inverse of the time evolution operator. Remember, this unitary transformation is not just an accidental, arbitrary one. We have chosen the inverse of the time evolution operator in the Schrödinger picture to carry out this transformation from the Schrödinger picture entities, that is states to new states, observables to new observables. The transformation is the inverse of the time evolution operator in the Schrödinger picture. Never forget it. So this is the first line. States are frozen. Now, what are the time dependence now of the new entities? How do they transform in time? Well, it's also easy. We take this definition and act on it by the d by dt each term, and let's see what we get. Okay. So d by dt ah of t is the time derivative of the first factor, u dagger, that's plus exponential. It brings down a I over h bar h, which I put to the left, and everything else is in here. What is everything else? U dagger asu, which is u dagger, u dagger asu, which is ah. I have done it in a rather fast way. If you cannot follow it, please ask, but this is true, really. Take the derivative and move h put it all the way to the left. Can I? Yeah, h and exponential of h commute. I could have put it to the right-hand side of the exponential of h, or to the left-hand side. I'm free to do so. Why this discussion? Operators are order-dependent entities. Therefore, you have to be careful where is the down-pulled thing is to be placed. That's the first term. Second term is the derivative moves in and acts on that as, so-called. But by default, we define the observables in the Schrödinger picture to be not to depend on time explicitly. Therefore, this doesn't pick any contribution from the derivative of time. And so time acts on the last factor. It brings down a minus I over h bar h. I put it all the way to the right. Can I? Operators commute within a function of them, so I'm free to put it all the way to the right. Minus I over h bar is put in here. U dagger as u and h is put to the right. Last factor is minus, therefore the minus I over h bar is a number. I put it all the way to the left. So what is this? I over h bar h ah of t. How nice. It is really this equation that we obtain to be satisfied by the now these new operators in the new picture. Well, as it stands, it requires for some discussion, because notice that A is taken to be at time t. And the same t appears in the right-hand side in the A. Perhaps you don't think that I'm using different A's to mean that they are different things. Just bad notation. It's the same. One is with the top and one is with the tip, but anyway. So we say, now this is the new equation of motion. As the states are frozen in time, they do not evolve. This is the equation of motion because that involves the time, that gives you the time dependence of A of t. And we have also seen at the beginning that expectation values are time, the same in any picture, whether it's states or the observables carrying a time dependence. Therefore, it doesn't matter. You solve this equation, you determine the time dependence, and whatever physical question you have been addressing, these are mathematical formalism of the physical phenomena. Whatever physical questions you have been asking in the Schrödinger picture, you can ask similar question of different mathematical nature to get the same result, of course, because physics is physics. You are trying to get numbers about the world. But it's this equation that you need to solve. I will demonstrate. But there are certain properties which I have to discuss first in order to be able to make use of that equation as this is pictured. So I have to put that aesthetically, saying that this follows. So these are the two equations. That's a good point to stop perhaps. We will continue the discussion after the break. Frozen in time, states are frozen in time, observables now evolve, and that's where the dynamics is. We will continue from this point.